let me write down the factor theorem. So theorem, again, it goes hand in hand with the remainder theorem. So factor theorem, and not sure I'm gonna be writing the words too much, but if I have to, I'm gonna write FT for that. Okay. All right. So what does it say? Suppose that we have a polynomial. So let y equal f of x be a polynomial, and let's suppose that we have that c is a real number, and let c be a real number. And there are two statements here. So the first one says that if c is a 0, then x minus c has to be a factor. Okay. So if c is a 0 of f, then x minus c is a factor of f. So what this means is that if you plug in c and you get 0, then you can conclude that f of x can be written as x minus c times something. That's something, we call it q. How do you find it? Well, you divide. You do division by x minus c, and you're going to find the quotient. Okay. Now, the other statement is that this also works backwards. Okay. But this is obvious, right? If x minus c is a factor of f, then of course c is a 0, right? Then c is a 0 of f. And this is clear because if you look at this expression and you see that that's what it means to say that x minus c is a factor, then of course if you plug in c into the function, you're going to get 0 because x minus c will give you 0 and the q doesn't matter. So you of course are going to get that f of c will be equal to 0. Okay. So number 2 is straightforward. We are going to be using it more in the sense of number 1, that you have your 0 and then you use it to come up with a factor for your function. Okay, questions? All right, so let's see. Let us do a quick example. Actually, a couple of quick examples here. So example number 1, let us use the factor theorem. So use the factor theorem to determine if the given polynomials are factors or not of a polynomial that I'm going to give you. So I'll give you some candidates and then you will tell me whether they are factors or not. So use the factor theorem to determine if the given polynomials are factors of the following, of the polynomial f of x equals 2x to the 4 minus 13x cubed plus 10 squared minus 25x plus 6. All right, and here are some candidates. Let's see, let's test out x minus 6 and let's test out x plus 3. Okay. All right, so we want to figure out whether let's look at x minus 6 first. We want to figure out whether x minus 6 is a factor or not of the function f, meaning whether we can write that as x minus 6 times something or not. And according to the factor theorem, all we have to do is verify the 6, whether 6 is a 0 of the polynomial or not. Okay, so and we can do that pretty quickly by by dividing. So let's do so. I'm gonna divide by 6. So this is by x minus 6. So let's do a quick synthetic division here. Remember, we're expecting 5 numbers. That's what we got. Let's do a process. So we bring the 2 down. We get 12, negative 1. That's negative 6. That's 4. That's 24. Negative 1, negative 6, 0. Okay. So we got remainder 0. What does that mean? So that means that the remainder is, remember, f of 6. That's remainder theorem. And what this is telling us is that this is equal to 0. So what can we say about x minus 6? Is it a factor or not? Is it yes or no? So It said yes for the first answer, right? So that means x minus 6 is a factor. Good. How about the next one? How about x plus 3? Is x plus 3 a factor? So to answer this question, well, we go ahead and we divide. So we need to divide by x plus 3. So remember, you need to put here x minus 3, right? And then we figure this out. So 2, negative 13, 10, negative 25, and 6. We activate the process. Let's see, 2, that will be negative 6. So we get here negative 19. That's going to be positive 57. So we get 67. So we already see that this doesn't seem to be working. So 67 times negative 3, what is that? Negative 201. So here we get negative 226. And for sure, when you multiply that by negative 3 and you add it with 6, you're going to get a number that's not equal to 0, right? So what do we get? So that's 18, 6, 7. So we get 678, looks like it. And then when you add these two guys, what do we get? Let's see, what is it that we're gonna get here? So we get 684. So the point is that this is the remainder, but this guy is different than 0. So this is not equal to 0. So what can we deduce? That x plus 3 is not a factor, right? So the answer is a big no. Okay, questions on how to test whether something is a factor or not of your polynomial. Yeah, so that's exactly what the theorem says. Read the theorem. So if c is a 0, then x minus c will be a factor. But also the other way around. If x minus c is a factor, that's number 2, then f, a factor of f, then c must be a 0. In other words, you have to have remainder 0. Because remember, the value of the function at c equals 0. That's the remainder theorem. Does that make sense? So you're going to have a factor if you get remainder 0 when you divide by that. You okay with that, Ramses? All right, good. So actually, let us now take advantage of this. So let us do our first factoring. But of course, I have to give you a hint. So let's see. Let us factor the following polynomial completely. So let us factor f of x, and this is so you see what's the dynamics in doing this. 2x cubed plus 7x squared minus 14x minus 40. So let us factor this polynomial completely. At this point, it's still hard for us, but I'm going to give you an extra information. Give you 1, 0, okay? So given that negative 4 is a 0. And actually, once we do this, then we can actually graph it. So why not? Let's go ahead and do it, and then graph the function f. Okay. But let's first focus on the factoring, because once you factor it, then it will be pretty straightforward to graph. Okay. So again, here I'm giving you a little hint. In other words, I'm already giving you 1, 0. All right. And with this information, we should be able to factor this polynomial completely. All right. Let's see. So solution. How do we do this? The fact that negative 4 is a 0, how does this help us? What does this mean? If we say that negative 4 is a 0, what does that imply according to our theorem? Who can tell me this? If negative 4 is a 0, what does that mean? What will be a factor for a polynomial according to the factor theorem? Anybody? No, what would be a factor? What would be a factor of our polynomial? You should not be telling me numbers. Read the theorem. Very good, Ramses. Would be x plus 4, right? Remember, that's what the factor theorem says. So if negative 4 is a 0, that means that x plus 4 is a factor. Remember, it was x minus c, so it will be minus 4. So x plus 4 is a factor of f. So that means that actually we can write down f of x, we can write that this is equal to x plus 4 times something, okay? So our goal now is to find q. So what do we do to find q? What do we do to find this q of x? All we have to do is we divide, right? We do division. If you already know that x plus 4 is a factor, all you have to do is then divide by x plus 4 and the result of the division. First of all, we better get remainder 0. And second, the quotient of the division will be our q of x, right? So let's go for it. So we're going to divide by x plus 4. And since here you can do it however you want, but synthetic division is the fastest, okay? So that's what I'm going to use. I'm going to use synthetic division. I'm going to divide the polynomial f by x plus 4. And we have to get 0 because we know that x plus 4 is a factor, okay? All right, let's see. So we bring the 2 down. This is negative a. We get negative 1. That's 4. We get negative 10. It's positive 40. So indeed, we got 0. That's good. We knew that. But now this is telling us what is q of x. Let's see. Who can tell me from here what's q? What's the quotient in here? Who can tell me this? What would be q of x? Very good, Maria and Frances. So it would be 2x squared minus x minus 10, right? So that means that our polynomial f is going to be x plus 4 times q. And what is q? 2x squared minus x minus 10, right? Okay, so then now that we have 2x, so remember, Emily, when you say plus minus x, that's just minus x, right? So if you say plus negative 3, that's just negative 3, for example. So plus minus x is just negative x. Right, good. Okay, so now remember, the problem says to factor completely, so we need to factor everything. So now let's go ahead and let's factor that degree 2 polynomial. You can do this however you want. I'm going to use try and error quickly here. So what can we do here? Let's see, we can put 5 and 2, and then negative here. That'll give me 4x minus 5x is negative x. So this will be equal to x plus 4 times 2x minus 5 times x plus 2. And we have our polynomial factor complete. Any questions on how we factor this polynomial? Okay, good. And then now that we have a factor, then let's finish it. Let's finish it because the whole point is that we're doing this so that we can graph it, right? So let's go ahead and let's try to sketch the graph of this. So remember, what do we need? We need to know the leading term. So now we graph. So let's see, what's the leading term? The leading term was y equal to, let's look at the original guy, is 2x cubed. So that's 2x cubed. So that already tells me that we're going to begin down here in quadrant 3 and we finish in quadrant 1. So we know the end behavior. So we come from down here and finish up there. Okay. Next, we need to know the zeros and the multiplicities. 0 together with multiplicity. So what are the zeros for this polynomial? Who can tell me the zeros? So we already have -4, right? That was given to us, and we can see it. What are the other two zeros? So we have -2, and what's the other one? Are you sure about that, Emily? Are you sure about 5? Good, 5/2. So 5/2, right? So those are two zeros. That the factor is 2x minus 5. So that means that 5/2 will be the 0. Okay? So remember, you have to be careful there. Okay, so those are our zeros. And what are the multiplicities? Multiplicity 1, everybody, right? So they are all cross points. So we are ready to graph. So let us do a quick sketch of this function. So let's see, what's the y-intercept here? Okay, y-intercept is -40. Well, we're gonna do a bad sketch because I'm not gonna go down to -40, but that's okay. I'm gonna put -40 right here. As long as you show the numbers, that's fine. We're just doing a sketch anyways. And then let's see, -2. Let's put it here. Let's put -4 here, and then 5/2. That's 2.5. So if this was my 2, then let's say 3 is here, so somewhere here. It's 5/2. Okay, and then we have to go through those 3 zeros. Multiplicity is 1, and because of the end behavior, we start from quadrant 3, and then some point we come back down. We have to go to -40. We need to come back up at some point, and we go through 5/2. And there you go. That's more or less a reasonable sketch of this polynomial. Again, it's not too reasonable because -40 is super down, but and I'm gonna do 40 lines here, so you understand that this goes way more down than what the picture is showing, but the numbers tells you what's happening. Okay, questions? So if you are given a 0, do you understand how to begin doing your work and keep on finding more zeros? At least with degree 3, that's everything, because notice that if you have a degree 3 polynomial and you know already 1 0, then you do exactly what we did. You find your q, which is a degree 2, and once you get a degree 2, you're basically done, because even if you cannot factor, you can use your quadratic formula to find the other 2 zeros. Okay, so really being able to figure out the zeros of the degree 3, you find one, then that's it. You found the other 2 as well pretty easily, either by factoring or using quadratic formula. You okay with this? All right. Now, of course, the hope is that you can do this without me telling you a 0, because when you are out there, nobody's going to tell you, hey, -4 is a 0, right? Your job is, given the polynomial f as it is, you have to be able to come up with all of this. In particular, you should be able to realize that -4 is a possibility for this guy to have it as a 0, okay? So that's what we're going to discuss next. How do we find candidates for the zeros of a polynomial, okay? And actually, I'm going to take advantage of this. What I'm about to show you is what we call the Rational Zeros Theorem, okay? So remember, I told you we cannot find every possible zero of a polynomial in every possible situation. And that's because if a polynomial has an irrational zero, we are not going to be able to find it nicely, okay? And we could be lucky, and maybe the irrational zero is going to be as a result of solving a quadratic, and then we're good. But in general, we won't be able to have a technique to find irrational zeros. But if the polynomial has a rational zero, you will be able to find it, okay? That's called the Rational Zeros Theorem. And what it says is the following. Let us take a look at the zeros that we found. For example, I guess 5/2 is kind of easy to see. So we saw that 5/2 was a 0. And notice that 5 is a factor of -40, because you can write -40 as -8 times 5. And the denominator, which is 2, is a factor of the leading coefficient, which is 2. In other words, I want you to focus on these two numbers. The numerator, the 5, was a factor of the constant term, and the denominator, which is 2, is a factor of the leading term, which is 2. Notice that this is also satisfied for the other two zeros, because -4, you can do it as -4/1, okay? -4 is a factor of -40, because it's -10 times 4, and 1 will be a factor of 2, because 2 is 2 times 1. And same thing with the other zero that we found, which was -2. You can think of it as being -2/1. -2 is a factor of -40, be -20 times 2, and 1 is a factor of 2. Okay? So what the rational zero says, the rational zeros theorem says, is that if your polynomial is going to have a rational zero of the form a over b, then a must be a factor of the constant term, and b must be a factor of the leading, of the leading coefficient. That's what the rational zeros theorem says. So let me write that down. Okay, and then you can use that to figure out candidates for your zeros. And then once you have your list of candidates, once you write all the possibilities for the rational zeros, you just start testing by doing division. Okay, that's basically what it boils down to. When the degree is high or the coefficients are big, this is a painful and long process, but you know it's what it is. Okay, that's what we have. All right, so let me write down the theorem. So theorem. This is called the rational zeros theorem. All right, so rational zeros theorem, and here is what it says. So let's suppose that we have a polynomial, and remember, a polynomial, how does it look like? It has a leading coefficient that we usually call it an, and then it has some, lower degree terms and so on, until we get to the last guy, which is a0. That's called the constant term. So be a polynomial with leading coefficient an, which is of course different than 0, and constant term a0. Okay. Also, let us assume that we have a rational zero. Okay, because if we don't have a rational zero, then of course this has no business here. So assume that p over q is a zero f. Okay, is a zero of f with p and q integers, pq integers. Here I'm saying that we have a rational zero. That's what a rational number is. It's a fraction with the total are integers. With p and q integers, then what we can deduce is the following. So number one, p, so the numerator of that zero is a factor of the constant term. Then p is a factor of a0, which is your constant term. And second, q is a factor of an, your leading term, your leading coefficient. And q is a factor of a. So this is what the zeros theorem says. And just to close this up, let me do a quick example. If you're given a polynomial, the first thing that you need to do is you need to be able to list candidates. Okay, so let us do that. So let's list all possible rational zeros of the following polynomial. Let's look at f of x equals -4 times x to the 4 plus 5x cubed minus 7x squared plus 8. So let's say that you want to analyze this polynomial and you want to figure out the zeros. We need to have a list of candidates so that we can start testing and seeing which one works and which one doesn't. Well, this theorem allows us to do just that. So remember, let us suppose we need to write down the factors of the constant term. So factors of 8. What are the factors of 8? Well, plus or minus 1. You have to look at the negative here. Plus or minus 2, plus or minus 4, and plus or minus 8. And then we need to also consider the factors of -4, which is the leading coefficient. That would be plus or minus 1, plus or minus 2, and plus or minus 4. And remember that the factors of 8, these are the candidates for the numerator. Okay, those are the candidates for P. These guys right here are the candidates for the denominator. So candidates for Q. So now let us find the possible zeros. So what are the possible zeros or the candidates for P over Q? Well, we're gonna borrow from the red list that goes in the top, the blue list that goes in the bottom. So for each number in the red list, we're gonna write all possibilities using the blue numbers in the denominator. So that would be plus or minus, then that would be 1 over 1, or plus or minus 1/2, that's 1 over 2, or plus or minus 1 over 4, because that's using 1 from the top and the numbers from the bottom. We are done using 1 from the red list. Now let's use 2 and repeat. And of course, if we have a repetition, we don't write it. So let's see. With 2 on top, we have 2 over 1, so that's plus or minus 2. Then 2 over 2, that's 1. We already have it. And 2 over 4, that's 1/2. We already have it, so there's no need to write. Let's go to 4 and repeat. 4 over 1, that's new. 4 over 2 is 2. We already have it. 4 over 4, that's 1. We already have it. And then we go to 8. So that's plus or minus 8, then 4 and 2, we already have it. So this right here is our list of candidates. So if this polynomial is going to have a zero, a rational zero, is in the list that you have in front of you. I understand there are a lot here. We have what? 1, 2, 3, 4, 5, 6 times 2, 12 possibilities, but that's better than not knowing anything. Because before we do this, we have no idea what are the zeros. At least we now have 12 candidates to try. And the way you try is, by dividing and seeing what works and what doesn't. So next time we're gonna refine this process a little bit more. The question is, how can we narrow this list a bit further? And that's what we're gonna keep on practicing next. But anyways, with this, you can actually start finding zeros and so on, okay? Okay, we are recording. Okay, so let's see. The last thing that we did last time was we wrote down the statement of the Rational Zeros Theorem, okay? That basically says that if you have a polynomial, then if this polynomial is gonna have a rational zero, then that rational zero is a fraction, and the top is gonna be a factor of the constant term, and the denominator is gonna be a factor of the leading term. So that's why you can just write all the factors of the constant term, all the factors of the leading term, make all possible fractions, and then you will get all possibilities for the rational zeros, and then your job is to start testing which one of these may work. Keep in mind that maybe none of these guys work, because it could be that all the solutions are complex, okay? Now, for example, this was a degree 4 polynomial. Maybe all the zeros are complex, so none of these guys will work. Or it could be that the zeros are all irrationals, so they're not going to be in this list, okay? So it doesn't mean that this is bulletproof, but at least it's something to start with. Okay, anyways, so let's do examples because we didn't really get to do any examples there. You have been working on this in the homework, but let's do some here. Okay, so example, find the zeros and graph. Remember, we cannot lose the skill of being able to graph. So find the zeros and then graph the polynomial. Okay. All right. So first, we're gonna take a look at this one. So f of x equals x cubed minus x squared minus 4x minus 2, and then we're gonna use a degree 4. Let's do 2x to the 4 plus 3x cubed minus 15x squared minus 32x minus 12. So let's go ahead and let's find the zeros of these polynomials, and then let's sketch the graph of these polynomials, okay? All right, so let's begin with A, and then we go with B. All right, so solution. So we have f of x equals x cubed minus x squared minus 4x minus 2. Okay, so the first thing that you should always do is, so remember, finding the zeros is really equivalent to being able to factor. If you can factor the polynomial, then you are done, okay? So you should take a look at it and see if you can factor this. We look at it and then you may say, oh, maybe trying by grouping, but unfortunately, if you try here by grouping, it's not gonna work, okay? So grouping is not going to do the job here. So what do we do? Well, let us try to see if we can find some zeros. So Maria, I could, it's just that it may take the whole class. So, here the point is not to do something that will take the whole class, because if you have large coefficients and large degree, it would take a while, and that's not really the point, right? So, for example, in an exam, I'm not gonna do that, right? In real life, it may show up, it may come up, but here the idea is to understand how to do it, and then if you have something with more coefficients or more degree, once you understand what's the process and what you need to do, it's just a matter of sitting down and doing it. But this could take you more than an hour doing it if you have a very complicated polynomial. Like I said, this is not an easy job. Okay, so I will stick with something that would be interesting. I think part B is kind of interesting already. Okay, no, in the quiz, I'm not gonna give you something crazy. If I give you something crazy, it's because I'm giving you something else that will make it very easy. And you will see in a second what I mean by that. Okay, you will see what I mean by that once we do all type of examples. But if I just throw a polynomial at you and ask you everything, which like I did here, it's not gonna be something crazy. For example, something like B is okay, and B is not that easy also. But something like B, I expect you to be able to do it from scratch, no problem. Actually, anything you should be able to do it. It's just that some problems will take more time, because if you put large coefficients, large degree, it's a nightmare. But a nightmare because it's tedious, not because it will be hard. Okay? Remember, long doesn't mean hard. It just means tedious. Okay. All right. So let's do this one. Okay. So let's try to at least get some candidates. And for this, we're gonna use the Rational Zeros Theorem. So remember, this we're gonna use factors of the top, of factors of the constant term, and then factors of the leading coefficient, which in this case is 1. Okay, so the factors of -2, these are plus or minus 1, plus or minus 2. Factors of 1, these are plus or minus 1. So in this one, we are kind of lucky because we have a nice little list, okay? So now we can write our candidates. So what are the candidates according to the Rational Zeros Theorem? Remember, the list on the top, that's the numerator, the list in the bottom, that's the denominator. So we have plus or minus 1 and plus or minus 2, because it's just over 1, okay? All right, so when the leading coefficient is 1, that's good, okay? It's nice because you're not going to get weird fractions. Okay, so now that we have this, then what do we do? Well, we have 4 possibilities, right? So let us check each of them. So let me tell you a quick thing. It's very easy to see whether 1 is going to work or not, okay? And because 1 will always be in your list, okay? So it's very easy for you to detect whether 1 works or not. And what happens when you plug in 1 into a polynomial? What happens is that all the x's become 1, and really what you're doing is just adding the coefficients. Does everybody understand this? So when you plug in 1 into the polynomial, all you do is you add the coefficients. So if you want to see if 1 is a 0, just look at your polynomial and add the coefficients. If you get 0, you found it. Otherwise, then you keep on looking at the others. So here, when we look at it, we see that if you add the coefficients, you're not going to get 0, because you will get 1 minus 1, that's 0, but then -4 minus 2, you get -6. So I know that 1 doesn't work, so I'm not going to even try. I already did it by looking at the polynomial. So I'm gonna try with -1, okay? And then here is what I do. I advise you to, you do this in a sheet of paper, write this in pencil instead of using pen, and do it very lightly. so you can reuse the same setup. Okay, here is what I mean. So the point is that, you know, synthetic division is fast, so you can do this setup. Let me put it like this. This setup, you don't have to do it light. You do it dark because this is always fixed, okay? Now, what you write light is this. I'm going to try -1. So what I do in red is what you should do very light, because if it doesn't work, you just erase that. And you reuse the same little table. Okay, so let's begin. Bring the 1 down, -1. We have -2. So that's a 2. Here, what do we got? We have -2. Okay, lucky. So we found 0. Okay, so we got 0. So that means that -1 was a root. If it was not, what I would do is I would just erase what I did in red and then try 2 and then -2. Do you guys understand this? All right. Anyways, we're lucky enough that -1 did the job. So now what does that mean? So what does it mean? We found that -1 is a 0. So far we have that -1 is a 0. -1 is a 0. So how do we use this to our advantage? What does that mean? It means that x plus 1 is a factor, right? Remember, that's a factor theorem. So now what we do is we factor a polynomial. So that means that the polynomial f of x, we can write it as x plus 1 times something else. What is that something else? Here is the information, right? This guy right here is the quotient. So that would be x squared minus 2x minus 2. Everybody okay with this? Are you guys okay with this so far? All right. Now, when you are dealing with degree 3 polynomial, you found 1 0 like we did now. The quotient, the result is going to be what's in red. After your factor will be quadratic, you're basically done. Because at this point, you can either keep trying the other two, or since this is quadratic, just use the quadratic equation. Okay? So I'm going to go ahead and use the quadratic equation because it doesn't look like 2 or -2 are going to do the job in here. Okay? So let's see, we plug in 2. Yeah, no, that's not going to happen. You're going to get a -2 for any of those two. So for 2, if you plug in 2, you get -2. If you plug in -2, you're going to get 6. So those two guys don't work, but that's okay, because since I'm looking for zeros, all I want to figure out now is when is x squared minus 2x minus 2 equal to 0. Okay, and now we work with this. All right, so to work here, because this is quadratic, the quadratic equation, I will just use the formula. So let me figure out the discriminant. B squared minus 4ac. That goes inside the square root. So that's -2 squared minus 4 times 1 times -2. So what do we get? So we get 4 plus 8. So the discriminant here is 12. All right. So we have 12 for discriminant. So that means that x is going to be -b plus or minus square root d over 2a. In our case, it means it's going to be -2 plus or minus square root of 12 over 2 times 1. So that's 2 plus or minus. So 12 is 4 times 3. So that's 2 square root of 3 over 2. And we can simplify all of these 2. So you get 1 plus or minus square root of 3. So you can factor out 2 on top and cancel with the 2 in the bottom. Okay? So we found the other 2 zeros. And as we know, because the degree is 3, that's it. We are expecting 3 zeros. Okay? So that means that f of x is going to be equal to x plus 1, and then the red polynomial x squared minus 2x minus 2, we can factor this as x minus the first 0, which is 1 plus square root of 3, times x minus the other 0, which is 1 minus square root of 3. So this is a good example because you see also how to factor here polynomials that, you know, do not factor nicely with rational numbers, but you can use irrational numbers if they show up in the factorization. Anyways, here we have the complete factorization of f. In particular, we see immediately what are the zeros. So remember, we always want zeros with multiplicity. And then we see that we found 3 zeros, namely -1, 1 plus square root of 3, 1 minus square root of 3, and they all have multiplicity 1. So when it comes to graphing, they are all cross points. Okay? All right. Questions? So now we're going to graph. We're going to sketch the graph. Are there any questions on this first example? What part? What part are you lost, Giovanni? Okay, so you figured out, so first we figured out that -1 is a 0, right? So that means that x plus 1 is a factor. What does that mean? It means that you can write your function as x plus 1 times something. That's what it means to have x plus 1 as a factor. So we do so, okay? So we write a polynomial f. Now we are here in this step. So we write f as x plus 1 times something. What is that something? Well, look at the division, right? When you did your synthetic division, the numbers that you have in there, those are the coefficients. So do you understand how to get the x squared minus 2x minus 2? Okay, so once you are here, then the next thing is, all right, we need to keep on looking for zeros. We already have -1, so I don't care about that now. That's x plus 1. So your focus, the other zeros, they are coming from our red polynomial, the other factor, x squared minus 2x minus 2. Are you okay up to here? So whatever it is that we need to do, it has to come from here now, because we already have x plus 1. That one gives me -1. Whatever else, whatever other zero is coming, is going to come from this other factor. All right, so now we focus on that. So you can think of this now as a new problem. Now, instead of the original polynomial, think about x squared minus 2x minus 2, and the question is, find the zeros of this guy. The idea is that this is easier. We lower the degree. Instead of degree 3, we now have degree 2. It turns out that when the question is about degree 2, you can just techniques about rational zeros or whatever, and just use the quadratic formula. The quadratic formula will tell you the zeros, and it will tell you whether they are rational, irrational, complex, or whatever. You just solve the quadratic formula. Yes, part B is a degree 4. Remember, we have two examples, Emily. Maria, sorry. Part B is a degree 4. So we will deal with that. Just let's make sure that we understand, because the idea that we're doing here is the same thing that we're going to do in the other. It's the same procedure. All right. The bottom line is that you're going to keep on doing this until you reach a degree 2 polynomial. Once you reach a degree 2 polynomial, you can claim yourself victory, because at that point you just throw in the quadratic formula to find the remaining 2 zeros. Okay. So let's see, if 2 was also a factor, would you add it and its quotient to the equation? What do you mean by 2 being a factor? You mean a 0? If 2 was a 0? Okay, if 2 is a 0, that would mean that x minus 2 is a factor. So I would do a similar thing with x minus 2. Okay? All right, so let's see. Wait, questions here. So if it is a degree 2, we use a formula. Yes, Giovanni. So remember, all we are doing is we're looking for zeros, right? So if you have a degree 2 polynomial, then don't suffer with all of these big theorems. Just use the quadratic formula. That's gonna tell you the roots. Okay. So really, the whole point is, if you have a high degree, you want to keep on testing and dividing and lowering the degree one by one until you get to degree 2. Once you are in degree 2, then you're good to go, because you can use the formula. The D is called discriminant. Remember, what's the quadratic formula? It's -b plus or minus square root of b squared minus 4ac over 2a. I just like to call that D, and I like to calculate that separate, because if you put in the radical, then it's a super big, and then all of these numbers inside the equation, it looks messy. So I like to calculate that number outside, also because that number tells me what to expect. Remember, a positive discriminant means two distinct real solutions. Negative discriminant means two complex solutions conjugate to each other. Discriminant equal to 0 means one solution with multiplicity 2. So that little number, this D right here, just by looking at it, it tells you a lot about the equation. That's why I like to calculate it by itself. And then once you have it nice simplified, then you put it back in the radical and you keep on going. Otherwise, it's very easy to make an algebra mistake. That's all. But you can do it, however you feel comfortable in doing. My recommendation is to calculate it on the side and then you put the number in the radical. That's all. All right, so are we good with how we found? And then once you have the zeros, do you understand how to write the factor form? Anyways, I'm going to give you the theorem down below, which is, it's called the linear factorization theorem. That tells you that every polynomial can be factored this way. All right, so basically you have your 0, then that means x minus that 0 is a factor. And that's what I used in this part right here. We found the two zeros, 1 plus square root of 3. So x minus 1 plus square root of 3 is a factor. And then 1 minus square root of 3. So x minus 1 minus square root of 3 is also a factor. Okay? And the reason why I don't put an a, like a leading coefficient, is because our leading coefficient was always 1. So this is a polynomial. Okay, anyways, we now have our three zeros, and we wrote the zeros, we wrote the multiplicity. Now the rest is, the rest is easy, so to speak. So we can now graph. So let's put our zeros. So we have -1 here, and then let's see, 1 minus square root of 3. Where is it? So let me make -1 bigger. Let's put a -1 here. Now, the square root of 3 is like 1.73. So 1 plus 1.73 is -0.73. So let's put it somewhere in here. 1 minus square root of 3. And then 1 plus square root of 3, that would be 2.73, more or less. So let's put it somewhere in here. Okay, so here we have a 0, a 0, another 0. The y-intercept of the function is important. The y-intercept is -2, right? You plug in 0 into the function, you get -2. So let's put that here as well. Let's say 1, -2. And now let's graph. So remember, what was the leading term of a polynomial? The leading term is x cubed. So in terms of the end behavior, it will look like x cubed. So leading term is y equals x cubed. So this is x cubed. So remember, this is how the end behavior looks. So we begin in quadrant 3 and we finish in quadrant 1. All right, so we come from here. At some point we need to turn, we go through. This is our y-intercept, go through that. At some point we need to turn, and then we go through 1 plus square root of 3. Again, how high we go, how low we go. Once you learn calculus, you will know precisely what this is. If you want to get a more accurate graph, you will need to plot more points, okay? But this is a quick sketch of what's going on. Anyways, question for the first example. So this is our polynomial f of x, okay? Questions? Yes, Sarah?
On the exam on the 23rd, that's due on the 23rd, are we gonna have problems like this? Are we gonna have like because I know homework we had problems.
Wait, what do you mean exam?
The quiz that we have due tomorrow.
Yeah, that quiz. So what happened with that?
Are we gonna have, because on the homework for 3.6 there were some problems that were really long and required us to figure it out without using the graph. If we were
they're not gonna be too long. I mean, there will be about listing the rational zeros and then finding zeros like what we're doing now. But like I said, it's not going to be something crazy. And remember, you have 2 chances to do the quiz. You have 2 attempts.
Okay.
So you should not wait until the last day to try the quiz for the first time, because then if you want to do it again, you may not have time. So,
yeah.
I strongly encourage you to, once you do a little bit of the homework, then you try the quiz. If you don't feel comfortable, then you know already what to expect, and then you do it again. But once you are more ready, so you prepare on what you need to prepare, and then you take it again. That's my advice.
All right. Thank you.
Yeah. But again, that's the quizzes. The exams, there is just 1 chance. There is no 2 attempts for the exams. But for the quizzes, this is just to make sure that you guys are understanding the little bits that we are discussing, okay? And not just to wait until the day of the exam to find out that you don't know something. That's the main reason for the quizzes, really. Okay, but is this example okay? Okay, Maria, what's going on?
So when we factor like the function completely, and we put x minus 1 plus root of 3, the second one, why we put x minus again? Wouldn't we put x plus 1
So
root of
again,
3?
the point is that if c is a 0, then x minus c is a factor, right?
Yeah.
That's what the factor theorem says. That's all I'm doing. So
Oh,
if
okay.
1 minus square root of 3 is a 0, then x minus 1 minus square root of 3 is a factor. That's all. Right?
Oh,
And
okay.
I'm literally using that. Remember, that was the factor theorem. Remember that we did
Yeah,
last time?
got it. Thank you.
Yep, no problem. Okay. All right. So is there no more questions on this? Let's see. Let's do the other one. The other one is more interesting. Okay. We have a degree 4 waiting for us. Let's see what we can do here. Okay. So let's do B. And that one was f of x equals 2x to the 4 plus 3x cubed minus 15x squared minus 32x minus 12. Okay, so again, we take a look at it. Maybe you are lucky and you can figure out a way of seeing if you can factor this. Not clear to me. So, for example, I would strongly advise you, if you see a common factor among the coefficients, let's say that all the coefficients you have super big numbers, but there is a common factor among those, please factor that out so that you can lower the coefficients. The smaller the coefficients, the nicer will be the process for you. Okay. Unfortunately, in this case, there's no common factor, but if there is, you should be looking for that. All right. Also, if you see that you can factor a variable also, like an x or something, do so, okay? In this case, we cannot. Okay, anyways, I'm gonna go straight to rational zeros theorem, so I'm gonna write down my candidates, okay? All right, so we need factors of negative 12, and here we need factors of 2. All right, so that's plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. And factors of 2, that's plus or minus 1, plus or minus 2. Okay, so let us make a list of candidates. So what are the candidates for the rational zeros? All right, so we're going to have plus or minus 1, plus or minus 1 half, using the 1. Now let's use 2. So plus or minus 2, then plus or minus 1, we already have that. We go to 3, plus or minus 3, plus or minus 3 half, then plus or minus 4, plus or minus 2, we already have it, plus or minus 6, then plus or minus 3, we already have it, plus or minus 12, and then plus or minus 6, we already have it. So how many candidates do we have? 1, 2, 3, 4, 5, 6, 7, 8. So we have a total of 16 candidates, right? Because each of these guys, they come positive and negative. So, even though 16 seems like a big number, it's actually nice. It's better than infinity, right? At least we have something to look at. Before you look at the polynomial, you have no idea what to do. Now we know what to do. It's just that it may take us a while. Okay, so I'm gonna do my setup. Okay, I'm gonna start trying here. So I'm gonna do my setup. Let's see, 2, 3, -15, -32, -12. And then we're gonna begin trying. So let's see. Can anybody tell me, will 1 work in here? If we put 1, is it gonna work? Okay, so please answer the question that I'm asking. Will 1 be a 0 here? So when I say work here, what I mean is we have a list of candidates for the zeros. Okay, there's a candidate for zeros. Remember. So will 1 work? I'm just starting from my list. You can start from whatever you want. I'm just gonna start with 1. What was a quick way to check 1? Add the coefficients. You look at your polynomial. When you add the coefficients, you get 2 plus 3 is 5. The rest of the guys are all negative and they're big. There's no way you're gonna get 0 with 1. Do you understand this? So I'm not going to even try 0 in my synthetic division. So I'm going to begin with -1. Let's see what happens. Let's see, 2, that's -2. Remember, you're gonna be doing this a lot, so make sure that you get practice so you can do it quickly. Okay, so 1, that's -1, -16, that's 16, -16. Then we get 16. Okay, we get 4. So that means -1 is not good. So we can cross these out of the candidates, erase. Remember, the stuff that is in red, you should write that very lightly, because if it doesn't work, just erase it. So you don't have to be writing a bunch of tables, and you can use the same. But you need to use pencil pen, then you will unfortunately need to write a new problem. Okay, so let's move to the next and repeat. So let's try with 1/2. All right, so we put 2 here, times 1/2, that's 1. So we get 4 times 1/2, that's 2. So here we get -13 times 1/2. We're gonna get -13 over 2. And then what do we get here? So -32 minus 13 over 2. So that would be 64 over 2. So 64 plus 13, that's 77, right? -77 over 2. And we can already see that we're not going to get 0, right? When you multiply, you're going to get -77 over 4. This is definitely not positive 12. There's no way we're going to get 0. So I know that positive 1/2 doesn't work. Let's try now -1/2. Okay. So try -1/2. Let's see. So we bring the 2 down. We multiply. So this time we get here -1. So this is a 2. Then here we get -1. So we get -16. Multiply, +8. -32 plus 8. That's -24. When you multiply, we get +12. Bingo. We found 1. Okay? So you found a 0. So what does this mean? The remainder is 0. So that means that x equals -1/2 is a 0. So what is a factor? So x minus 1/2, x plus 1/2, sorry, is a factor. Everybody okay with this? Do you understand what's going on so far? Okay, so now what I always do, what I recommend you to do is, instead of keep on trying, you could keep on trying down the list to see if you find more guys. My advice is to go ahead, factor out your polynomial, and then you write the new polynomial that you get, the new factor, and then do the problem with that one, because this will allow you to lower down your list. Because when you factor, you may get lower coefficients. Okay, maybe not, but maybe yes. So that's my advice to you. In other words, instead of keep on trying here, since I already found a 0, what I'm gonna do is I'm gonna factor my polynomial. So I know that this is gonna be x plus 1/2 times something. What is that something? Well, I'm gonna use this right here. Okay, so what's the polynomial that we get? We get 2x cubed plus 2x squared minus 16x minus 24. Okay, and really now the question is to focus on the red polynomial and keep on factoring down. Notice that we reduce the complexity of the problem because we were in degree 4. We now narrow down the problem to a degree 3 polynomial. So now we work on that one. Yes, Sarah.
Oh no, I don't have a question. My hand was still raised. My bad.
Oh, okay. All right. So now we're going to work on the red polynomial. Okay. But before we do that, notice that all the coefficients here, they are even numbers. So I'm going to factor out the 2. Okay. So I'm going to do so. Just, to lower the numbers. The smaller the numbers, the better. So x squared, then minus ax minus 12. That's good. And actually, notice that then I'm going to take that 2 that I factored out, and I'm going to distribute it into my first factor, so that instead of plus 1/2, we have a nice 2x plus 1. Okay. Again, this is just a cosmetic preference. I like to take a look at this one better. So 2x plus 1, and then what we have left here is x cubed plus x squared minus ax minus 12. Okay, so here we have our f. Now we're going to direct our attention to this polynomial, the degree 3 polynomial. So now we repeat the process, okay? So let's write down a new list. So a new list of candidates. This, of course, is going to be a sub-list of the original one that we did, okay? But maybe we can, eliminate some of those elements in that list above. For example, those fractions that are showing up in the previous list, they are not going to show up anymore, because notice that the leading coefficient is 1. When the leading coefficient is 1, we're not going to have fractions as rational zeros. There will be integers, because the factors of the leading coefficient, those are the ones that go in the bottom, and the factors here are just plus or minus 1. So that's good. That's good news. So that means that plus or minus 3/2, we don't even have to worry about it. That we had before, we don't really have to worry about that now. Did you understand that observation that I made? Did you guys understand that? Okay, so let's write down then the new list of candidates. We know plus or minus 1 doesn't work because it did not work at the beginning. It's not going to work now because any zero of the red polynomial has to be a zero of our polynomial. So we ignore plus or minus 1. We ignore plus or minus 1/2. Now let's be careful. The reason why I'm ignoring negative 1/2, positive 1/2, we can ignore it because it was not a zero anyways, originally. But the reason why I'm ignoring negative 1/2 is because it cannot be a zero of this new one, because like we said, this new one cannot have fractions of 0, because the denominator is only allowed to be positive or negative 1. Okay, so that's why I'm not trying negative 1/2 again, because it could be, remember that a 0 comes with multiplicity. That means it will be a 0 more than once. Multiplicity is higher than 1. Okay, so you have to watch out for that. Okay, anyways, so my candidates then are going to be the factors of negative 12, taking away plus or minus 1, so that would be plus or minus 2, plus or minus 3. We skip the 3/2, and then plus or minus 4, plus or minus 6, plus or minus 12. So at least we have a shorter list now to consider, and let's begin. So I'm going to prepare my new table. So 1, 1, negative 8, negative 12, and let's activate the process. Let's put a 2. So 1, that's 2, 3, 6, negative 2, negative 4. Okay, doesn't work. So we know that 2 doesn't work. How about negative 2? Let's try negative 2. So we bring the 1 down. We get negative 2. That's negative 1. Positive 2. Negative 6. Positive 12. Bingo. Here we found another one. Okay, so negative 2 is a 0. And notice that once you find this one, we are actually done. Let's see, who can tell me why is it that we are actually done? Anybody? Who can tell me why we are actually done? Very good, Maria. Because now when we factor out the x plus 2, we're going to get a quadratic. And at that point, you can just, solve it with the formula or factor it if it can be factored, whatever the case may be. Okay? All right, good. So from here, it follows that negative 2 is a 0. So x plus 2 is a factor. Okay, so that means then, so remember our polynomial f, it already had the 2x plus 1. So now we're going to factor the red part, okay, which was the cubic. That one will be x plus 2 times, and then the remaining part, let's change the color, will be then an x squared minus x minus 6. And again, where am I getting that one from? Well, by looking at the result of our synthetic division. Okay, questions about this so far? Okay, and now, we repeat the process by looking at the blue polynomial, but because it's degree 2, we know that we can just do the formula and we're done. Now, in this case, instead of doing the formula, I'm just going to factor, because this is something that we can factor easily, right? Two numbers whose product is negative 6 and the sum is negative 1. We can easily find numbers. Can you tell me what they are? How do you factor the blue polynomial? Negative 3 and positive 2. Good. So that's negative 3, x minus 3, x plus 2. So here we didn't even need to use the formula because we were able to factor it easily. Now notice that x plus 2 showed up twice. So that actually means that negative 2 is a 0 also, of course, of the blue polynomial. So that's why when you reduce it down a degree, you should not ignore completely the factor that you took out already, because that 0 could still be in your new polynomial. Like in this case, negative 2 is still 0 of the blue polynomial. So let's write down f. So f is going to be 2x plus 1 times x minus 3 times x plus 2 squared. So this is our polynomial f. So in particular, we can now write the zeros together with their multiplicity. Okay, so what are the zeros? We have negative 1/2, we have 3, and we have negative 2, right? Those are the zeros that we found, because 3 is coming from the factor x minus 3. And what are the multiplicities? Well, we have 1 for negative 1/2, 1 for 3, and multiplicity 2 for negative 2. So that means these two guys are cross points when we look at the graph. And what's going on with this one? What do we know about negative 2? What happens there? What's the graph going to do at negative 2? What type of zero is this? It's a touch point, right? This is a touch point. And now, with this information, then we graph. Let's see, before I sketch this graph, questions. Are there any questions on this example? Up to now, do you have a question on how we found the zeros? Okay, good. And so now we graph. So remember, we have a polynomial f of x, which is, I'm going to write the factor version here. And as we know, what was the leading term of this guy? This was 2x to the 4 plus lower degree, guys, and then the last term was minus 12, okay? And I'm not writing the meter because I don't really care about the meter now, because for graphing purposes, we just need the zeros, and we need to know the leading term, we have it here, and also the constant term is important because that would tell you the y-intercept, okay? All right, so we have what we need here, so let's go ahead and do a sketch. So that's x and y. Let's see, let's put a zeros. So we have negative 1/2. So let's say that this is 1. So negative 1/2 is going to be here. Then we need to put -2. Then we need to put 3. So 3. Okay, so here, 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 and then y-intercept will be -12. Okay, so I'm not gonna do 12 little ticks, so whatever, I'm just gonna put it down here. We are sketching anyways. And then the end behavior, let's see, what's the end behavior? Can anybody tell me in terms of quadrants, in what quadrant, sketching from left to right, what quadrant do we begin and what quadrant do we finish? According to the end behavior of this function. Do we begin in quadrant 2 or in quadrant 3? And do we finish in quadrant 1 or in quadrant 4? For example, in the previous example, we began in quadrant 3 from left to right and we finish in quadrant 1. What would be the end behavior here for this one? Okay, but that's the end, but what's the beginning? Where do we begin? Let's see, what tells you the end behavior, guys? All right, so the end behavior is given by the leading term, right? So we have 2x to the 4. So it's an even power. So what does that mean? And the coefficient is positive, so you're not flipping anything. So how do power functions look like when they have an even power? Remember, they have this parabolic behavior, yes? So what do we do? So we begin in second quadrant and we finish in first quadrant, right? So we come from up here and we finish up here. Everybody okay with this? Begin in second quadrant and finish in first quadrant. Okay, so now that we know that, then we can start graphing. So we're coming from above somewhere. So now what happens at -2? We need to touch, okay? So we're coming from above, we hit -2, we bounce back up. At some point we need to turn. We go through -1/2 in a linear way because the multiplicity is 1. We need to go through -12. At some point we need to turn back up. And then we go through 3 in a linear way as well because multiplicity is 1. So here is more or less a sketch of the graph. Okay, questions? All right, good. So now, of course, as you can see, you know, this is a little bit tedious. Having a big list like this is a pain, even though it's nice because at least you have something to look at. It's still too much. So it would be nice if we have ways of cutting down this list. Okay. Of course, there are more sophisticated theorems that allows you to do just that. That allows you to cut down this list in a certain way. So let us try to discuss this a little bit, okay? So what I want to do now is I want to give you some theorems that may make you more comfortable when it comes to finding zeros. But basically what we have, these are the rudimentary tools that you can then try to tackle any polynomial that comes your way. Unlucky cases would be when the zeros are, you know, complex zeros or irrational zeros. Then unfortunately, that's what makes this business really hard. Okay, because they not always are rational zeros. Anyways, let me just I'm gonna keep on giving you tools, and always keep in mind that you know there is always all of these things are always taken with a grain of salt, because once again, think about our friend x cubed plus x plus 1. No matter how hard you try, you're not gonna be able to find exactly the zeros of this polynomial. Okay, so you know it's just what it is. As I said, I mean, using calculus, you can see that we have only one real zero. The other two are complex zeros, but that real zero that you find, remember, this will be rational, and what we did last time was we approximated the zero by using intermediate value theorem over and over again, approximating decimal places. But if you want to find it exactly, that's not going to work. Therefore, it will be very hard to find the other two complex zeros. because you cannot factor it because you don't know exactly what the zero is. You could approximate, but finding the zeros exactly, that's out of reach right now. Are we good with this? So what I'm telling you is that it doesn't mean that you will be able to solve every single problem. Of course, the one that you will be given to do, I don't know, in an exam or in a quiz, yes, those will be problems that you can solve. But don't go out there saying, "Oh, I know how to find any zeros," because someone's gonna look at you and tell you, "Okay, try this guy," and then all your techniques will fail here. What you can do is go back to the basics and use intermediate value theorem and approximate as we did last time.